This is the 7-3 alpha lesson. Now, you got to be careful because we're going a little bit out of order. I don't know if I relabeled the PowerPoints in Canvas or not, but if I did not, I don't remember this. We're doing day 2 first. And we're doing the last thing is the gamma lesson. They started off as day 1, right? But you have to understand what's going on. This says disc and washer. The disc, a washer is a disc. Make sense? Except the washer has a hole in it. So we're doing problems with a disc that does not have a hole in it and one that does have a hole in it. And we're doing them all of that today. And then tomorrow we will show you what FRQ looks like in terms of a disc or a washer. And then we'll move on. But you need to understand everything we do today will be perpendicular to the axis of rotation. You got root x. We're going to do this. We're going to rotate root x around the x-axis and create this 3-dimensional nose cone. And we want the volume of that. Now, what did we do so far? Well, let's do this. Let's back up and do this in 2 dimensions. So at your desk, you find the area under the curve from 0 to 4, 2 dimensions. And you should have what's on the board, and you can't see it over your home, but you should have got 16/3 square units, unless I made a mistake. Did I make a mistake? You could have, because I mistake. So what are we saying? The height of this curve from 7-2 is the y vector. So how tall is it? It's y1 take away, upper take away lower. It's y1 take away 0. So you'd have root x take away 0. Yes? Which is x to the 1/2. Anti-differentiate, and you get x to the 3/2 divided by 3/2 is times 2/3. Put 4 in here. Square root of 4 is 2. 2 cubed is 8. 8 times 2/3 is 16/3. Plus the constant, subtract, put 0 in there, and you would get 16/3. Yes? Make sense? Awesome. Now, do the problem dy. You have to get the same answer. Yes? So how can I do the problem dy? Set it up. And I am going to put the camera up here so you can see it. Well, if you're at home, I don't know how well you can see this. I'm trying to, the red work is dx, and the purple work is dy, but both times you're getting the same answer. We're getting 16/3. And what happened in the red work? We did upper take away lower. What happened in the purple work? We did right take away left. So right take away left here, we're going from 0 to 4, would be the line. X equals 4, take away the curve. And the curve is y equals root x, so x equals y squared. Is this logical? You have to get the same answer or you made a mistake. Now, you could have done it, got the same answer, and they could both do the same thing and be wrong, but that's unlikely.
Why is it right by front?
Why is this going to be? Meaning, we're taking the positive value, take away the negative value. The greater value, take away the lesser value. So it's the same thing as we do upper, take away lower. Higher, greater versus lesser, subtract lesser. And right take away left is higher, take away lower. They're just being consistent. But if you did it backwards, you would get the same answer. It would just be negative. Okay? So you're going to get enough practice with this that you wouldn't do it backwards. But the issue is, and I will put this on that, I'll put this on that paper that we give you. It's always going to be upper take away lower or right take away left. And we're going to get into more involved problems. You have to keep that straight. Okay? So that would be 16/3. That would be the square units, the area. We're going past that. We're going to do it in 3 dimensions. So what's on this board up here in red and purple is the 7-2. 7-2 red is alpha, 7-2 purple is beta. Area between curves. So now what are we going to do? The volume of the cone. So we're going to have this cross section. Now in the top picture, it looks just like what we did for the area. In the top picture, we're saying height times width, add them up. You good? That's what an integral is. It's the sum of all these heights of these rectangles times how wide they are, add them up to get the total area. In the bottom picture, what this cross section would actually look like would be a disc. You can think of it as a coin. And we're going to find the volume of one coin and then add them up. So, the height or the surface area of the coin. The surface area is a circle. So it's pi r squared. It's like a quarter or a nickel. Okay? It's pi r squared. And then how thick is the coin? Think like you imagine standing a nickel up on your desk. In this case, it's dx thick. So we've got pi r squared, which is the surface area, times how thick it is, which is dx. Now, think about this, please. Where did they get this? It's pi. The surface area of the coin is pi r squared. The radius in this case would be the height of the curve take away 0. See, it's pi r squared. So this is the radius. We don't want the diameter of the coin.
You want the radius of the coin. And the radius would be the y value. Take away 0. But because we're doing the problem dx, we have to substitute with y equals, which is root x. From 0 to 4, what happens? Well, root x, the quantity squared, just gives you x. We're putting these values in there. Now you got to be careful because we have to anti-differentiate. Power rule reverse. X squared over 2 times that pi. And you would get, ready, 16 times pi over 2 plus the constant, subtract 0 plus the constant. You would get 8 pi. Cubic units. So what we're doing here is this. We're doing this purple exercise. It says this. This is what we're doing first. That's on the PowerPoint. What we will do in the PDF is put a hole in the disk. So you got to be able to do this first. We're doing all of that today. And then spend tomorrow doing one FRQ. So what you have to do is say, between now and tomorrow, yeah, I'm okay with the disk, and then the washer trying to confuse me, we go back over it. Because we've got 45 minutes, and we have committed 5 of those minutes to do one component of an FRQ. Now, certainly it's going to take you longer than 5 minutes, but it's the first time you've seen this. But there is plenty of time tomorrow to address your questions. You need to think about that. I'm going to pretend I get it when I don't. That would be good. So the volume is 8 pi cubic units. Now, I think this is confusing, so I really wouldn't even write this down. When I give you this paper, which will be the beginning of next week, I will summarize this for you. But this is saying the volume equals pi r squared, and the radius would be the y value, dx. But you can't write y in there. It's always going to be y squared, but it would depend on what the function was, and they would be different. So that's why they wrote y squared. Because in our case, it was root x squared, but it could be something else. But it's always going to be what y equals. The height. And they're saying, okay, well, suppose we did the problem dy. That's fine. This dy would be x squared dy. Because that'd be the radius. But we're not going to worry about that yet. So here's a problem that is, well, yeah, we are going to. Here's a problem that's dy. But it's very visual. So you got this picture. You're looking at it? And it is a lampshade. And we want to find the volume if you had a solid lampshade. Well, it wouldn't be a very good lampshade if it was solid, but you could put the light bulb underneath it. But we want the volume of that shade. So we're saying here's, ready? X depends upon y. And we're going from 1 to 4. In the first example, they took that shape and revolved it around the x-axis, and now we're taking this shape, revolving around the y-axis. What do? We put these numbers in for 1. 1, 2, 3, 4 are the inputs. 1, 2, 3, 4, those are the outputs. So ready? So we have to do this to plot it. We're going to point 1, 1. 1 over root 2, which is 2 over root 2. Do you recognize that? Oh, sorry, root 2 over 2, comma 2. Root 3 over 3, times 3. 1/2 times 4. The plot, if you start plotting them on the Cartesian plane. But now we're doing, ready? Look what happened. See, this is what this means up here. This perpendicular symbol means everything we're doing today is perpendicular to the axis of rotation. So this cut here, dy, is hitting the y-axis at a right angle. It's perpendicular to the axis we're rotating it about. And if we back up to the cone problem, see, we rotated this function about the x-axis. And our cut hit the x-axis at a right angle. Everything we're doing today is perpendicular. So what do we get? We need the limits in terms of y. 1 to 4. Pi, what's the radius? This goes with Smith and asked. We're going to do right, take away left. The radius would be 1 over root y subtract 0. That would be the radius. Right, take away left. So we would have from 1 to 4 pi r squared dy. Square it. What do we got? Pi times ln y, which is, put the values in, ln 1 is 0. Now, I wouldn't go there. I wouldn't rewrite this as 2 pi ln 2. I'd be fine with 100% correct on the AP test if you wrote that as ln 4 times pi, 100% correct. If you understand where the ln's coming from. No, maybe yes. You're anti-differentiating that. Pi is a constant. You want to use the power rule in reverse. You have y to the negative 1. Negative 1 plus 1 is 0. Divided by 0, dead end. Natural log is the bridge between the power rule with negative x, the power rule in reverse with negative exponents, and the power rule in reverse with positive exponents. So we're going to go here to the textbook and look at example number 3. Okay. Now, this is way harder than what you've been doing. You got to pay attention. So I have this. I'm in the first quadrant. And what are the borders? The y-axis, cosine x and sine x. So cosine x and sine x will meet when cosine x and sine x are the same, which happens at pi over 4 radians. Yes? So the graphs are meeting. So my limits, dx, would be 0 to pi over 4. Now what? Pi r squared. Except what? When you rotate this, look what you got. You got this picture over here. You have a hole in the graph. That's a washer. See, the problems we've done so far don't have washers. It was just a disc. So it looks like this. And we want this shaded area inside. So what would you get? You would get pi times big R squared, which would be the whole thing. and you would subtract pi times little r squared, and you would be left with the donut. Is it logical? It's 100% logical. But when you go in one day from the disc to the washer, it's a lot to get your mind around. And we're telling you that we are chopping our steps and doing the FRQ tomorrow for you to say, wait a minute, this made sense to me, this did it. You can do this. Ready? It's an A, B, and B, C topic. You're going to get this stuff, like they're almost done. They're like a couple days behind you, and they'll be done in February, the curriculum. But they do volumes. You're going to do stuff that they won't do. This is part of Calc 1. So, we would have, ready, over here, take the pi out, and we would have pi. Big R squared, take away little r squared. So how do I know what's what? Well, big R would be whoever curves higher. So big R would be the cosine wave, which you see is going down, and little r would be the sine. So this pi big R squared subtract pi little r squared can be written as pi cosine squared take away sine squared. All right, I don't really care about answers today. I care about you setting the problem up correctly. You getting it that far. Numerical answers are secondary.
Why are we using the area of the circle to find the volume?
Okay, why are we using the area of the circle to find the volume of the cone? Is that a logical question? Sure, because we're saying the surface area of the circle, pi r squared, is the surface area. And then if we expand it by its thickness, which we're calling dx or dy, then we would have the volume of one coin. And if we put all the coins together, when we anti-differentiate, the sum of all those, volume. But that's what we need people to do, is think out loud. I'm not sure where this is coming from. We're saying that the surface area in 2 dimensions is the area of a circle. And we make it in 3 dimensions, we multiply it by the thickness. So if it's dx times the surface area. Then we add them all up, that's the anti-differentiation component. Except this question is about to get way hard, which is good for you. Now, this, first off, here's the question from the end. Well, once you think about this, we'll come back to this tomorrow. This is a copy of what I'm going to give you. You're going to get a hard copy, and I'm encouraging you to use the hard copy on exit tickets and to use the hard copy on the assessment when we get there. So here's part, and it's in Canvas already. So they didn't give you the hard copy of it, but this is in the Chapter 7 Canvas folder. If the cross section's a washer, because we're saying what? Discs are subsets of washers where the inner circle is 0, or the radius is 0. If small r is 0, then we do it the same way as we do the washer. Perpendicular. These 2 lines are, if it is discs, these 2 lines, if they're washers, always do upper take away lower, right take away left. So this prompt is on here. But here's where this question becomes more challenging. Now, if you are at home, you're going to stay with us until we do this problem. Here's the question. Here comes the cosine wave. Here comes the sine wave. They meet at pi over 4. Then we take this thing and we reflect it over the x-axis. And if we go perpendicular to the axis of rotation, there's a hole there. So we would have pi big R squared take away little r squared. And the volume, is what Smith had asked, the volume equals the sum of the surface area times how thick it is. Add up all of them. So in this question, we would have from 0 to pi over 4, because that's where they meet, pi cosine squared subtract sine squared, which doesn't equal what's on the left. You cannot distribute an exponent over subtraction. Wrong, right. Does that make sense? Please don't do this. Please don't say it's pi, big R take away little r, the quantity squared. That's not correct. Because you cannot distribute an exponent over subtraction. You have to FOIL it. This is wrong, that's right. So we could do it on the calculator. So I typed math 9. See what I typed? From there to there, it gives me an answer, which is pi over 2 cubic units. This is a non-calculator question. And here's the challenging part of the problem. You can't anti-differentiate this. Because what is this? This is the derivative of a difference. Same thing as a sum, which is the sum of the derivatives. But if mu is cosine x, I can't anti-differentiate that unless I had d mu. Yes? Which is negative sign. J n. Except it's an artificial problem. It's built to work out. And what is this? This thing equals cosine 2x is double angle. Oh, nobody told me there's going to be pre-calc in this class. So if you have issues remembering your double angles, I put them at the end of the document. The cosine of alpha plus beta, the sine of alpha plus beta, double angles, which are when alpha beta are the same, all that's there. That's what Mrs. Bratz went over with you, but that's been a while. So, we rewrite the problem as cosine 2x. Now, if you're at home, right, as long as you see this far, where mu is 2x, so d mu 2x is 2, so I need 2 dx. I put a 2 there, I put a 1/2 out front, so that's where that pi became pi over 2, and you're going to get the answer. If you're at home, you're dismissed to do the exit ticket. But I am telling you, first off, this, in order to understand this, you have to understand it in 2 dimensions. And secondly, tonight's a big night for you in terms of homework. Because you got to do enough of these problems, this is logical to you. Because we can have all the time we have built in tomorrow, and if you don't know what to ask, you're not really going to make progress on this. This is fun. Okay? This is something that is challenging, and then when you get your mind around it, you're like, it's really good for your self-esteem. Wow, I can do this. Like, it's a hard thing to do. The people, you know what proportion of the population understands this? Way less than 1% of the entire population understands this. So, here's what happened. Mu is 2x. D mu 2x, d mu dx is 2. So I need 2 dx, and I differentiate this. So I put a 1/2 out front to balance multiplying by 2. Cosine is a derivative of sine. So it will give you sine 2x when you anti-differentiate it, times that pi over 2. From pi over 4 to 0. So I put pi over 4 in here. When you double pi over 4, you get pi over 2. The sign of pi over 2 is a 1. Put 0 in there. You get the sign of 0, which is 0. You get 1 times pi over 2, which is pi over 2 cubic units. Now, this is sending us to problem 17. And all we're going to do for 17 is set the problem up. So I'm going to draw the picture for you. There it is. And you're just going to build the question. I don't care about the answer.